Okay, welcome everyone to our third International System Safety Workshop. I'm John Sloan with the U.S. Federal Aviation Administration, the Office of Commercial Space Transportation. And as a reminder, as we go ahead with presentation today, feel free to ask questions, use the chat box and type them in, and then we'll try and get to those during the presentation. Today's speaker is Chris from our System Safety Branch. And let's begin. Chris, over to you.
All right, thank you. Next slide. So this is an overview of the things that we're going to discuss over the course of the 4 workshops. Today we're going, next slide. Today we're going to discuss 450-109, 450-143, and additional safety critical requirements. Next slide. 450-109 applies to the use of a flight hazard analysis as a hazard control strategy to derive hazard controls for the flight or phase of flight of a launch or reentry vehicle. Additionally, any hazards associated with computing systems and software are further addressed in 450-141, and we'll discuss that in part 4 on Thursday. A flight hazard analysis must identify, describe, and analyze all reasonably foreseeable hazards to public safety resulting from the flight of a launch or reentry vehicle. And I believe we discussed how to determine reasonably foreseeable hazards in 450-107 on last Thursday. Section 6.1 of the AC discusses the objective of a flight hazard analysis, which is to identify key system design and operations data, document the overall system safety risk to the public, and determine the necessary hazard controls or mitigations to ensure the residual risk meets acceptable criteria. It's important to note that system safety risk documented in the flight hazard analysis is typically expressed in qualitative terminology. However, there may be sufficient operational history and subsystem analysis to express the risk in quantitative terms. Next slide. Section 6.2 of the AC discusses how a flight hazard analysis differs from flight safety analysis. The most obvious being that risk stated in the flight hazard analysis is different than as stated in the FSA. Both flight hazard analysis and FSA are somewhat interrelated, but intentionally independent analyses that are both integral to the overall hazard control strategy. A flight hazard analysis must ensure the likelihood of any hazardous condition that may cause death or serious injury to the public is extremely remote. Whereas the objective of the FSA is to characterize the overall risk to the public caused by the operation as a whole in consistent quantitative terms. And it's also important to note that compliance with 450-101 safety criteria, which is the quantitative terms of the FSA, does not relieve the operator from completing the flight hazard analysis when it is determined as a hazard control strategy. Next slide. Section 6.3 of the AC discusses methodology. Per 450-103B1, the flight hazard analysis methodology must be defined and should be accomplished via the documented system safety program, which was discussed last Tuesday. The data documented in the flight hazard analysis is utilized to ensure public safety as defined by the documented system safety program. Next slide. Section 6.4 of the AC further discusses aspects of a flight hazard analysis. Flight hazard analysis may be utilized as a hazard control strategy if it's determined as such in 450-107B, but it is also mandated by 450-107C for a flight or phase of flight if the public safety hazards cannot be mitigated adequately to meet the public risk criteria 101A, B, and C using the other hazard control strategies of physical containment, wind waiting, or flight abort. The use of the flight hazard analysis to derive hazard controls provides flexibility that does not currently exist or did not currently exist under prescriptive requirements of Part 417, but is broadly consistent with Part 431 and 435, which is more of a system safety based approach. Flight hazard analysis should be performed early in system development along with the rest of the system safety, including the functional hazard analysis. During system development operational conceptualization to define the system safety risk to the public in order to positively influence design and operations decisions. And the flight hazard analysis products must continue to be maintained through the life cycle in accordance with 109C and E. Next slide. Section 6.5 of the AC discusses formal traceability of system safety hazards, which is critical for tracking the data in system safety analyses. Formal tracking methods should be established to show direct connections between all aspects of the system safety hazards to the public. The table A1, the template of table A1 in the AC shows the types of information that an applicant should provide to demonstrate traceability, as shown here on these images. Next slide. Section 6.6 of the AC discusses system safety hazards and their relation to software safety or computing system safety. In accordance with 451.41a, which will be discussed on Thursday, if the flight hazard analysis identifies software or data utilized in a subsystem or the integrated system as a potential hazard source of hazard controls, then the applicant should further conduct a software hazard analysis to identify computing system safety items and assess their level of criticality. Per the guidance of the associated AC, software hazard analyses identify potential software faults and their effects on the computing system and the system as a whole, as well as mitigation measures that can be used to reduce the risk associated with computing systems. Next slide. 451.09b states that a flight hazard analysis must identify, describe, and analyze all reasonably foreseeable hazards to the public resulting from the flight of a launch or reentry vehicle. Each flight hazard analysis must identify all reasonably foreseeable hazards associated with the launch or reentry system relevant to public safety, assess each hazard's likelihood and severity, ensure that the likelihood of any hazardous condition that may cause death or serious injury to the public is extremely remote, identify and describe the risk and elimination and mitigation measures required to satisfy the above, and document the risk elimination and mitigation measures achieve the risk of paragraph B3 through validation and verification. Next slide. 109C discusses new hazards. An operator must establish and document the criteria and techniques for identifying new hazards throughout the life cycle of the system. 109D discusses completeness prior to flight. For every launch or re-entry, the flight hazard analysis must be complete, and all hazards must be mitigated to an acceptable level in accordance with 109B3. And 109E discusses updates. An operator must continually update the flight hazard analysis throughout the life cycle of the system. Next slide. This is a color wheel that helps to pull all of the requirements of 109 together, and as such shows the iterative closed loop process of the system safety analysis. Next slide. Section 7.1 of the AC discusses the first part of 109, identifying hazards. The hazards referred to in a flight hazard analysis are the system safety hazards to the public that occur from a system failure. The starting point for identifying system safety hazards to the public is the functional hazard analysis, which was discussed and is required and by 45107B, and it was discussed on last Thursday. And the functional hazard analysis decomposes system functions and assesses the end effect resulting from each mechanism of each function during each phase, excluding mitigation and redundancy. For traceability, the proper identification of system hazards to the public should be demonstrated from subsystem and component functional failures to their causes, and 2, subsystem and component functional failures to their respective system safety hazards to the public at the system and mission level. Next slide. Continuing on identifying hazards, data from and beyond the functional hazard analysis could include system failures leading to system safety hazards to the public, including all applicable failures identified in the functional hazard analysis. Other possible failures not in the functional hazard analysis should be included if new ones are uncovered when considering public safety. An operator should decompose systems beyond what is in the functional hazard analysis to identify the causes of system failures. Such supplemental data could come from a fault tree analyses or failure modes and effects analyses. And additional analysis tools could include preliminary hazard analysis, system requirements hazard analysis, subsystem hazard analysis, human error analysis, and so on. There will likely be multiple potential causes for each system failure. Each potential cause of a failure should be specified to a level of detail and where it is possible to apply a mitigation. Next slide. Section 7.2 of the AC goes to the next piece of 109B, which is assessing likelihood and severity of each hazard. This is done in order to determine the associated system safety risk. The characterization of each system safety risk allows for determining the necessity and proper application of any additional mitigation actions. Resources for system safety risk assessments. Suitable assessment severity categories and likelihood levels criteria should be determined for each specific program. Section 8.1 of AC 45103-1 provides guidance on assessing and documenting system safety risk, including severity categories and likelihood levels. Risk assessment with respect to system safety hazards to the public generally utilizes qualitative statements. However, there may be sufficient data to utilize quantitative terms, as discussed earlier. Next slide. Continuing with assessing severity and initial likelihoods, the FAA encourages but does not require the utilization of a systematic development process that allows for a baseline assessment of pre-mitigation risk for each hazard. The FAA recommends that applicants who choose not to utilize pre-mitigation risk assessment strategy discuss the appropriateness of their development process and any risk assessment assumptions during pre-app consultation. This strategy may not be acceptable with all programs. Irrespective of the applicant's development process, post-mitigation risk assessment should be performed to determine the residual system safety risk to the public. And in accordance with B4, risk assessment should be performed at the appropriate levels, primarily the subsystem and component level and system and mission level. Risk assessment at these levels allows for greater insight into the effectiveness of mitigations and verification specific to each cause of each functional failure, resulting in a system safety hazard to the public and appropriate application of component, subsystem, system, and mission mitigations and verifications. Risk assessment traceability should demonstrate from system, subsystem, and component level risk assessment to system and mission level risk assessment. Next slide. Section 7.3 of the AC discusses mitigating risk to acceptable levels. Per B3, the risk elimination and mitigation measures must reduce the risk to the acceptable level. Proper mitigation process, mitigating risk does not change severity of the hazard, only the likelihood. If there is a change in severity, it should be documented as a new risk, and that is consistent with traditional system safety. The applicant should develop a risk acceptance criteria. Risk acceptance is determined by comparison of final assessed system safety risk against established acceptance criteria. Suitable risk acceptance criteria must be determined for each specific program and documented in the system safety program, compliant with 103, and additionally utilizing the guidance of the AC. To ensure proper acceptance of risk associated with system safety hazards to the public, the associated residual risk should meet the established acceptance criteria, and the rationale for acceptance should be documented. Next slide. Section 7.3 of the AC continues for a baseline of risk acceptability. Per B3, the baseline standard for risk acceptability of system safety hazards to the public is to ensure the likelihood of any hazardous condition that may cause death or serious injury to the public is extremely remote. And as documented in the AC for 45103, extremely remote should be considered so unlikely it can be assumed occurrence may not be experienced with a likelihood of occurrence less than 10 to the negative 6 in any one mission. And that is at the system and mission level. Next slide. Section 7.4 of the AC discusses identifying and describing risk mitigation measures. These measures must be identified and described, initially deemed for system safety risks that are initially deemed unacceptable. In accordance with B5, the risk elimination and mitigation measures must document reduction to the acceptable qualitative level of 109B3. Consideration should be given as to whether proposed risk mitigation measures introduce new hazards. To allow flexibility, the FAA has not mandated any particular mitigation approach. Where possible, the FAA expects the utilization of existing industry standards for mitigations. Next slide. Traceability for risk mitigations should be demonstrated from subsystem and component functional failures to their causes to their respective mitigations. Subsystem and component functional failures to respective system safety hazards to the public at the system and mission level. Subsystem and component level risk assessment to system and mission level risk assessment. And system safety hazards to the public at the system and mission level to their respective mitigations. Next slide. System safety design order of precedent in conjunction with 882E, must identify the following mitigation approaches in order of decreasing effectiveness, starting with eliminating hazards through design selection, moving to reducing risk through design alteration. If not, incorporate engineered features or devices, provide warning devices, and lastly, incorporate signage, procedures, training, and PPE. The first priority should be to eliminate system safety hazards to the public through appropriate design selections or operational decisions. Unacceptable system safety risks to the public that cannot be eliminated must be reduced to acceptable levels. Potential risk mitigation measures or methods include design or operate for minimum risk, incorporate safety devices, provide warning devices, or develop and implement procedures and training. Next slide. Section 7.5 of the AC further discusses validation and verification The reduction of system safety hazards to the public via the risk mitigations at the appropriate various levels must be validated and verified. Validation evidence must demonstrate that the risk elimination and mitigation measures achieve the risk level of 109B3, and the evidence must be provided to the FAA in accordance with 109F1. Validation determines whether the implemented mitigation measures and their respective verification methods are sound. The validation effort ensures that each mitigation and verification is unambiguous, correct, complete, and consistent. The validation process evaluates that each mitigation measure and respective verification is well understood and operationally and technically feasible. Next slide. Continuing with verifying risk mitigations, verification is the process of identifying and producing verifiable and measurable evidence for ensuring that the respective mitigation measures adequately support the documented reduction of system safety risk to the public. Where possible, the FAA expects verification of mitigation measures to utilize existing industry standards. Essential information for verification includes identification of specific methods used to verify the mitigation measure, identification of specific evidence to be produced, and an indication of closure based on successful completion of the specified method with production of adequate, verifiable, and measurable evidence. Next slide. Continuing again, verification methods include analysis, component, subsystem, or system test, demonstration, and inspection. And these are 4 acceptable methods of verifying mitigation measures. Next slide. Verification artifacts generally include, as discussed before, documented evidence from design analysis, test data, and inspection reports. Ideally, all mitigation measures should be validated and verified by the time of application submittal. However, the FAA recognizes that applicants may not have the ability to verify all mitigations prior to submission of an application. In those instances, an acceptable verification closure strategy should be documented with expected completion dates. However, this strategy should be provided to the FAA with adequate time to review the closure status of the verification evidence prior to initiation of the applicable licensed activity. Next slide. Traceability for verifications should be demonstrated from subsystem and component functional failures to their causes, to respective mitigations, to adequate verifications, subsystem and component functional failures to respective system safety hazards to the public at the system and mission level, subsystem and component level risk assessment to system and mission level risk assessment, and system safety hazards to the public at the system mission level to their respective mitigations to adequate verifications. Their iterative approach of V&V, the V&V process is a comprehensive closed-loop iterative process to be used in all phases of the life cycle of the system. Any mitigation that fails V&V cannot be relied on for elimination or reduction of the system safety risk to the public. Next slide. The appendix of AC 45109-1 includes a template. This template documents in one page the items discussed in section 7. Beginning from left to right, the data from the functional hazard analysis is utilized to document the subsystem and component level assessment. The causes are determined from fault tree analyses, FMICAs, or other system safety or reliability type analyses. The first piece is to identify and verify the mitigations to specific causes of functional failures at the subsystem component level. And then the residual risk from that subsystem component level risk assessment is then applied to the associated hazard at the system and mission level. And then residual risk is mitigated, and those mitigations are verified to determine the overall residual system safety risk of public safety hazards, which must meet 109B3. And through all of that is traceability through the analysis of all the data. The next few slides are a blow up of these sections. So if we go to the next slide, it shows a little closer the first piece, which is the data from the functional analysis and the additional data from other analyses to determine the causes. Next slide. Moving into the subsystem component level assessment. Next slide. And then finally ending in the system mission level mitigations. Again, with traceability throughout the entire analysis. Next slide. 45109C again discusses new hazards. New hazards must be identified throughout the life cycle. And updates, 109E, updates must be continually captured in the flight hazard analysis throughout the life cycle. Foreseeably, in regards to updates from lifecycle data, foreseeably data gained during design, manufacture, test, and operation, including the discovery of anomalies and faults, usually has impacts to flight hazard analyses and other system and the system safety case in general. Necessary data should be identified and approaches should be implemented to detect anomalies and failures in order to improve the flight hazard analysis. Information gained during assembly and operation of components, subsystems, and next level systems contributes to further understanding of the overall system and mission and may lead to additional updates to the flight hazard analysis. A process should be implemented to update the flight hazard analysis and the residual system safety risk assessment to reflect knowledge gained during the life cycle of the integrated system and mission. Next slide. 109D, completeness prior to flight. The flight hazard analysis and the system safety case must be closed and complete, and all hazards must be mitigated to an acceptable level in accordance with B3. Accuracy via the system safety program. In accordance with 103B and D, methods to detect flight anomalies and system failures and processes for evaluating post-flight data must be defined in the documented system safety program. Flight hazard analysis should adequately reflect the data gained from these methods and processes to ensure accuracy throughout the life cycle of a launch or reentry system. Next slide. Application requirements. Applicant must submit first the flight hazard analysis products of paragraph B1 through 5, which are shown in the and part of the color wheel, and the criteria and techniques for identifying new hazards throughout the life cycle of a launch or reentry system as required by paragraph C. Additionally, there is the appendix for a system safety template for the 109 flight hazard analysis shown on the next slide. And this was discussed earlier in this presentation, where we walk through how the data is how the data of the flight hazard analysis is documented. Next slide. So summarizing the key topics in the discussion of 109, all reasonably foreseeable hazards must be identified, along with the causes for each hazard associated with the launch or reentry system relevant to public safety. Each hazard must be assessed for severity, likelihood and severity at the subsystem component level and system mission level. Risk elimination and mitigation measures must be identified and described at the subsystem and component level and system mission level. Verification and validation must be documented to ensure likelihood of any hazard condition achieves a risk level of 109B3. Criteria and techniques for identifying new hazards must be established, and 109 flight hazard analysis is continually updated throughout the life cycle and must be complete prior to each flight. Next slide. Any questions? It was a lot of information. Some of it may be straightforward, but some of it may be questionable. Give it a minute. Okay. Well, if you think of anything, let me know.
Okay.
Go to the next section. Now we're going to discuss 450.143, safety critical system design, test, and documentation. Next slide. 143 applies to all safety critical systems except for highly reliable flight safety systems that meet the requirements of 450.145, or safety critical systems for which an operator demonstrates through its flight hazard analysis that the likelihood of any hazard condition specifically associated with the system that may cause death or serious injury to the public is extremely low pursuant to 109B3. And in other words, if a safety critical system is identified, and as we discussed last Thursday via 450.107 or via additional system safety analyses, that safety critical system must meet 143 unless it is demonstrated that the hazard associated with that safety critical system failure meets the acceptable criteria of extremely remote in 109B3. An AC for 143 is forthcoming to provide an acceptable means of compliance. AC 450.143-1 will cover non-highly reliable flight safety systems. AC 450.143-2 will cover all other safety critical systems. And this AC is currently under development and is subject to change upon publication. Next slide. 143B discusses design. An operator must design safety critical systems such that no credible fault can lead to increased risk to the public beyond nominal safety critical system operation. 103C discusses qualification testing of design. An operator must functionally demonstrate the design of a vehicle's safety critical systems at conditions beyond its predicted operating environments. And those environmental test levels must ensure that the design is sufficiently stressed to demonstrate that system performance is not degraded during the operation. Acceptance of hardware, 103D. An operator must functionally demonstrate any safety critical system while exposed to its predicted operating environments with margin is free of defects, free of integration and workmanship errors, and ready for operational use. And the operator must combine in-process controls and quality assurance process to ensure functional capability of any safety critical system during its life cycle, service life. Next line. 103E, life cycle of safety critical systems. The predicted operating environments must be based on conditions predicted to be encountered in all phases of flight, recovery, and transportation. An operator must monitor the flight environments experienced during the system components to the extent necessary to validate the predicted operating environments and assess the actual component life remaining or adjust any inspection period. Next slide. This is a table of all of the application requirements in 143. For 143, for each of these application requirements, the table provides additional guidance on what data needs to be provided for those application requirements. Next slide. To summarize, the key topics of 143. First, you have to determine the applicability of 143 requirements. You have to design for credible faults of safety critical systems. You have to perform qualification testing and acceptance. And you must account for environments encountered during the life cycle. Any questions on 143 or second call for questions on 109? Okay, moving along to additional safety critical requirements. Next slide. As stated in the preamble to the final rule, the applicant's identification and proper management of safety critical systems is fundamental to mitigating potential hazards and ensuring public safety. The FAA will work with an applicant if it believes the applicant has failed to identify all safety critical systems. The potential failure of safety critical systems is integral to the FSA, and vulnerabilities of safety critical systems must be accounted for in the flight commit criteria, hazard analysis, lightning protection criteria, management of radio frequency to prevent interference, and communication plans. In short, system safety analysis is utilized to guide the application and depth of the safety critical requirements. Next slide. Safety critical requirements include 450.45 E3II, which calls out the location of all safety critical systems. 450.115, flight safety analysis methods. The scope of the analysis must account for all reasonably foreseeable events and failures of safety critical systems. 451.49, safety critical personnel requirements. Safety critical personnel must be identified, the tasks must be identified, and the safety critical personnel must be trained, qualified, and capable of performing those safety critical tasks. 450.151, work shift and test requirements. Must ensure that an operator documents and implements rest requirements to ensure safety critical personnel are physically and mentally capable of performing their safety critical tasks. 450.153 on radio frequency discusses how an operator must ensure that radio frequency interference does not adversely affect performance of any flight safety system and or safety critical system. 450.155 readiness. The procedures must ensure readiness of the safety critical personnel, systems, software, procedures, equipment, property, and services. Next slide. 450.157, an operator must implement communication procedures and ensure that the communication networks, the personnel identified in A1 have direct access to real-time safety critical information, and an operator must record all safety critical communications that support safety critical systems during each countdown. 450.163 lightning hazards. A vehicle, if A2 is utilized, a vehicle must be designed to protect safety critical systems in the event of a direct lightning strike or nearby discharge. 450.165 flight commit criteria should include confirmation or must include confirmation that any safety critical system is ready for flight. And finally, 450.213 pre-flight reporting. A licensee must file a schedule that identifies each review, rehearsal, and safety critical operation. The schedule must be filed and updated and allow for the FAA personnel to participate in the reviews, rehearsal, and safety critical operations. Next slide. And that's additional safety critical requirements. So as discussed today, we discussed 45109 flight hazard analysis. We discussed 45143 safety critical system requirements for design, test, and documentation, their applicability, how their applicability is determined, and then what those requirements are. And then we went further to discuss the additional safety critical system requirements sprinkled throughout 450 that are all tied back to the identified safety critical systems, primarily through the functional hazard analysis and other system safety analyses. Any questions?
Okay, I don't see any questions. We'll give it another few seconds. For anyone who has any questions, please send them. While we're waiting for that, we did record today's session, and we'll send out a note later on the link for that, so that can be accessed later. And our fourth and final workshop is 2 days from now, Thursday afternoon, US time. And let's see if we got any questions. I don't see any. Chris, any final comments? I think we're done.
No, I guess if you have any questions, just reach out to your group and we can follow up.
All right, thanks everyone for joining us, and this concludes our workshop, and have a good day.